The universe has rules. Galaxies drift apart. Gravity pulls inward. The cosmos expands. But in the deepest voids of space, something is breaking the game. A silent anomaly, dragging entire clusters of galaxies against all known forces toward some unseen horizon. No cosmic structure should be this powerful. No known physics explains this. So what's out there? A ghostly supermassive attractor from another dimension? The gravitational echo of a long-dead universe? Or something even more unsettling? Proof that our reality is just a small current in a far darker, stranger ocean? This isn't just a mystery. It's a crack in the foundation of cosmology itself. Imagine standing on a quiet hill. The night sky is heavy with light. You look up and feel small. Now imagine that every bright smudge out there is not random. Imagine billions of galaxies drifting together. They glide in the same direction. They move like leaves caught in a steady wind. This is the idea that shook a calm corner of cosmology. It is called dark flow. The name sounds mysterious. The mystery is simple to state. Clusters of galaxies appear to share a common motion. They seem to head toward a small patch of sky near the constellations Centaurus and Vela. The motion is not tiny. It is hundreds to 1,000 kilometers each second. It stretches out to enormous distances. The team that first reported it said the flow reaches at least to scales of 1 billion light years and possibly far beyond. How do scientists see such a thing from here on Earth? They use a subtle trick. Hot gas in galaxy clusters scatters the faint afterglow of the Big Bang. This afterglow is the cosmic microwave background. When the hot gas moves with the cluster, it shifts the light in a way we can try to measure. This is the kinematic Sunyaev-Zeldovich effect. It leaves a tiny dip in the microwave map at the cluster position. Alone, the effect is too faint. But by stacking many clusters and using clever filters, the small motion can emerge from the noise. This was the basic idea behind the measurements. The original team used data from the WMAP satellite and large catalogs of X-ray bright clusters. They looked for a dipole in the microwave signal at cluster locations. They found one. It lined up. It pointed roughly in the direction of Centaurus and Vela. The strength of the dipole suggested a coherent flow of clusters at speeds of several hundred kilometers per second and possibly approaching 1,000 kilometers per second. Why does this feel so wrong to many people? Because our universe is expanding. On large scales, the motion of things is dominated by that expansion. Galaxies move away from each other. Peculiar velocities exist, of course. They are motions on top of the expansion. But the standard picture says these peculiar motions should fade at very large scales. They should not all line up toward one small patch of the sky across 1 billion light years. A true dark flow would ask us to rethink what lies beyond our observational horizon. It would hint that something very large and very distant tugs on matter inside our visible patch of the universe. This is where the story gets human. Science is not one voice. It is many voices speaking back and forth. Soon after the first claims, other researchers checked the numbers. Some found reasons to doubt the strength of the signal. Careful analyses pointed out how correlations in the microwave data and the details of the filters could change the significance. One well-known critique argued that when these correlations are properly counted, the detection drops to the level of ordinary chance. Then the Planck satellite came along. Planck made the most detailed maps of the microwave sky to date. Its team applied tests similar to those used earlier. Their conclusion was cautious. They reported no statistically significant detection of a coherent flow at the level claimed by the first team. That result pushed many people toward the view that the original signal might be due to subtle analysis choices or to underestimated uncertainties. The debate did not end there. Some groups re-examined Planck and WMAP together. They argued the dipole signal seen earlier is present in both data sets and not tied to a single instrument. They also found that the signal correlates with the most massive clusters, which are the ones that should show the strongest kinematic effect. Their view is that the evidence is still open to interpretation and that more work is needed. If dark flow is real, the implications are profound. One idea is that a huge lump of mass lies outside our visible universe. Its gravity could pull on matter inside our patch. Another idea is more exotic. Some theorists have suggested that features of the early universe, perhaps predating the last phase of inflation, could leave a large-scale tilt in the motion of matter. Others have wondered whether collisions or interactions with regions beyond our horizon might leave a signature like this. All of these ideas push against the safe limits of standard cosmology. That is why the claim, if true, would be revolutionary. Yet the wiser view is patient. Extraordinary claims need extraordinary proof. The signal reported so far sits at the edge of what our instruments and methods can robustly do. Different teams get different answers. Some find a hint, some do not. Large catalogs of cluster velocities from other methods and new microwave surveys keep arriving. Each one chips away at the uncertainty. New techniques try to extract the kinematic signal in cleaner ways. Simulations test whether known effects can fake the result. For the curious reader, the journey is a model of how science works. Someone notices something odd. They publish a careful analysis. Others check. Some find support. Some find problems. Better data and better tools arrive. The truth moves closer. For now, dark flow remains a question. It is a hint more than a law. It asks us to look again at the oldest light in the sky. It asks us to measure better. It asks us to imagine the very large and very far. If you remember one thing, let it be this. The universe can surprise us. Sometimes that surprise comes wrapped in subtle signals. Sometimes it takes 10 years of argument to know whether the surprise is real. Imagine you are learning to read the oldest light in the sky. That light is faint. It comes from when the universe was a baby. We call it the cosmic microwave background. It is the afterglow of the Big Bang. It fills all of space. It carries a map. That map is written in tiny heat differences. Satellites make that map for us. They sit far from Earth. They look at the whole sky. They measure temperature with great care. Two of the most famous are WMAP and Planck. They made maps with tiny details. Those details tell us about the early universe. They also give a steady frame of reference. Galaxy clusters help us read the map. They are the largest bits of matter that glow in X-rays. They hold hot gas. That gas scatters the baby light as it passes by. This scattering changes the light a little. It makes a small mark in the microwave sky. That mark is called the Sunyaev-Zeldovich effect. There are two parts to the effect. One part is thermal. It comes from hot electrons and raises or lowers the light in a steady way. The other part is kinematic. It comes from motion. When the whole cluster moves, it gives a tiny Doppler shift to the light. This is the kinematic Sunyaev-Zeldovich effect. It is the judge of motion at the largest scales. Why does this help measure speed? Because the cosmic microwave background acts like a calm sea. If a cluster moves across that sea, it leaves a ripple. We try to see that ripple. The ripple is very small. It is often buried under other signals, so we need many examples. We need a long list of clusters. We need clean maps from satellites. We need careful filters and clever math. When we stack the signal from many clusters, the tiny ripple can add up. That gives a single clearer motion signal. There is also a deep idea about frames of reference. We live in a moving patch of space. That motion shows up as a dipole in the full sky map. Cosmologists use the microwave background as the cosmic rest frame. They measure other motions against it. If a group of clusters share a motion that shows up as a common dipole at their positions, then we can speak of a bulk flow. The whole method depends on that cosmic frame being steady and well mapped. Turning tiny heat differences into velocities takes care and craft. First, the maps must be cleaned of known signals. This includes the thermal Sunyaev-Zeldovich effect and galactic dust. Next, special filters reduce the noise that comes from the random pattern of the microwave sky itself. Then we measure the temperature dipole at each cluster position. We combine those measurements across the whole sample. The result is an estimate of the average motion of the group. Each step can change the final answer. So teams test their filters with simulations. They check how the method responds to false signals. Numbers matter. A single cluster gives a weak result. 100 clusters give a better one. 1,000 is better still. The first teams that searched for a coherent motion used samples of many hundreds of clusters. They reported a dipole that was hard to ignore. This claim sparked close study by other groups. Some found support. Some found the effect disappeared when they changed the filters or the way they handled errors. This is the nature of work at the edge of what instruments can do. Precision is the watchword. Tiny biases can mimic emotion. Beam shapes, calibration drift, and correlated noise all can nudge results. The way a team selects clusters can also matter. So can the map used and the mask that hides bright parts of the sky. Because of this, many teams ran independent checks. Planck made the most detailed maps to date. Its analyses placed tight limits on any large-scale bulk motion found by kinematic methods. Those results pushed the debate into a careful back and forth. At the same time, new work shows we can detect kinematic signals in other ways. Pairwise statistics and cross-correlation with galaxy surveys give a different handle on the same physics. Teams using optical galaxy catalogs and new microwave maps have found kinematic signals consistent with small-scale flows. These studies show the method can work when applied with varied tools. They also show the path forward. For a person who is new to this, the steps are clear. We map the cosmic microwave background. We find and list massive clusters. We clean the maps and use filters. We stack signals and estimate a dipole. We measure velocities and test them with simulations. We check for biases and repeat the work with other data. That is the method. This foundation is strong. It is also delicate. It depends on excellent maps. It depends on clean cluster catalogs. It depends on careful statistics. When all pieces come together, we can ask a bold question. Is there a coherent motion across scales that we did not expect? That question is the reason teams keep refining the tools. It is why new surveys matter. It is why students and engineers build ever finer instruments. If you walk away with one idea, let it be this. Seeing the universe is an act of patience. It is also an act of craft. Tiny signals teach big lessons. To read them, we must sharpen our eyes. We must measure with care. We must test again and again. Only then will we know what the sky is trying to tell us. They began as careful observers. They were not chasing headlines. They wanted to measure how galaxy clusters move. They worked at places like NASA Goddard and nearby labs. Their leader was Alexander Kashlinsky. His collaborators included skilled X-ray astronomers and data analysts. They used maps of the oldest light in the sky. They also used catalogs of bright X-ray clusters. Their idea was simple and brave. A moving cluster slightly shifts the baby light that fills the universe. That shift is tiny for one cluster, but many clusters can show a pattern when combined. What they did felt like stacking faint whispers. They put together hundreds of clusters. They looked at the microwave sky at each cluster spot. They used filters to mute the louder patterns. What remained was a faint dipole at the cluster positions. A dipole means a direction of motion across the sky. The result surprised them. The clusters seemed to share a common motion. They pointed toward a small patch of sky. The motion reached out to huge distances. If true, it would not fit the simple picture most cosmologists expect. They did not claim a miracle without care. They published their methods and their data. They wrote a paper with a careful technical companion. They explained each step of the filtering and the error checks. Others read the papers with equal care. Science is a conversation. Some respected researchers found problems. A careful statistical critique argued that the apparent signal could be driven by correlations in the sky maps and by underestimated errors. That work raised the chance that the detection was a fluke. Kashlinsky and his colleagues answered. They dug deeper into their error estimates. They then published a detailed study of what could go wrong. They showed how some of the earlier critiques missed steps in the way the map dipole was handled. They said their dipole remains when those steps are done correctly. The debate moved to the next big map. A new satellite with better data checked the claim. The Planck team used different methods and instruments. Their analysis placed tight limits on any large-scale bulk flow and did not confirm the strong effect at the level first reported. That was not the last word. A later reanalysis by members tied to the original work compared both WMAP and Planck maps with an expanded cluster catalog. They reported that the dipole at the cluster positions is present in both data sets and that the signal correlates with the most massive clusters. They argued that this reduces the chance that the effect is a simple map artifact. At the heart of the matter sits a single technical phrase. The dipole found at cluster pixels is the primary claim. It is not a loud signal. It is a subtle asymmetry that points away, explaining that asymmetry needs careful work on filters and on error budgets. Different teams using different filters have reached different answers. This story shows two things about real science. One is the courage to publish an odd result. It takes nerve to say the sky behaves in a way that challenges common models. The other is the patience to let many teams test the idea. Some tests support it, some do not. Both kinds of results move us forward. If you trace the timeline, you see steady work. The first papers appeared in 2008, with technical detail published soon after. The team expanded its catalogs and methods over the next years. Critical responses came in 2009 and 2010, and led to careful rebuttals and error studies. Look up. The sky is a map. It is written in the oldest light. That light is the cosmic microwave background. It arrived when the universe was very young. It is almost the same in every direction, but it is not perfectly even. Tiny hot and cold spots trace the first seeds of structure. Those tiny spots are what scientists read like a weather map. Galaxy clusters are islands in that map. They hold vast clouds of hot gas. That gas scatters the old light as it passes through. The scattering leaves a faint fingerprint on the sky. Part of that fingerprint comes from how hot the gas is. That is the thermal Sunyaev-Zeldovich effect. Another part comes from the motion of the cluster itself. That is the kinematic Sunyaev-Zeldovich effect. The kinematic part is the one that can tell us about motion. The kinematic signal is tiny. It hides under many louder things. There is the random pattern of the microwave background itself. There is noise from the instruments. There are emissions from our own galaxy, so scientists must clean the map. They use filters that mute known patterns. They mask bright parts of the sky. They design statistics that pick out the tiny ripple that motion would make. These steps are subtle. Each choice can shift the result. That is why the work began with stacking. One cluster shows almost nothing. Many clusters together can lift the faint signal above the noise. Teams assembled hundreds of X-ray bright clusters. They looked at the microwave temperature at each cluster position. They then combined those spots into a single measurement. The result is an average motion for the whole sample. This is the practical heart of how the unmeasurable can become measurable. The first strong claim came from the WMAP era. Using WMAP maps and a large cluster catalog, a team reported a coherent dipole at cluster positions. That dipole looked like a bulk flow. It pointed toward a region near the constellations Centaurus and Vela. The implied speeds were large. They were hundreds of kilometers per second, and in some estimates approached 1,000 kilometers per second. The reach of the effect was vast, stretching to scales of hundreds of megaparsecs. The claim stirred a careful response. New data arrived from the Planck satellite. Planck made the cleanest all-sky microwave maps to date. The Planck collaboration tested the same methods. Their published results placed tight limits on large-scale peculiar velocities. They did not confirm a strong bulk flow at the level first reported. That finding cast doubt on the simple picture of a vast, coherent motion. Not everyone agreed. A later analysis that compared WMAP and Planck data argued that the dipole at cluster positions appears in both maps. That work also found the signal to be linked to the most massive clusters. Its authors said this reduces the chance that the result is a simple artifact of one instrument. So the community found itself with two careful and different readings of the same sky. How strong is the signal, really? That is the key question. Statisticians and cosmologists looked at the error estimates. Some argued that correlations in the microwave maps and in the filters reduce the significance of the original detection. Others rechecked the catalog selections and the way the dipole is computed. Different approaches gave different answers. Some found high significance. Some found results consistent with chance. This debate shows how fragile a faint result can be when it lives near the limits of our tools. Velocity numbers matter. If the effect is real, the speeds are not small. They are much faster than the motion of our local group around the Milky Way. They are large enough to be surprising in the standard cosmological picture. Those numbers are the reason the claim drew attention. They are also the reason the claim demands careful cross-checks. Direction matters too. Across many cluster samples, the reported motion points to a similar patch of sky. That consistency is what makes the finding more than a random scatter. If many independent checks keep finding the same direction, then the case grows stronger. If not, the pattern could fade. So far, the direction has been one of the central pieces of the argument on both sides. Distance is the other hard part. The original work argued the flow extends to scales that are enormous. Translating those scales into human terms gives numbers like 1 billion light-years and more. If a pull acts on such scales, it raises deep questions about what lies beyond our visible patch of the cosmos. But pushing a signal that far makes the measurement harder and the error budget larger. Today the evidence is mixed. Some careful studies find a hint that survives new maps. Other careful studies find nothing that cannot be explained by noise and bias. The truth sits with the data and with the method. Better maps, larger cluster catalogs, and new statistical techniques keep arriving. They will sharpen the picture. They will tell us if the sky whispers a new truth or if the whisper fades under scrutiny. If you listen to the story as it stands, you hear both caution and awe. Caution because tiny patterns can mislead. Awe because the idea that many galaxy clusters might drift together is a strong and lovely image. Reading the cosmic map is hard work. It is also one of the most honest ways to learn about the world beyond our sight. The debate over dark flow reminds us that science is slow and steady. It moves by testing and by retesting. It trusts careful data more than bold claims, and it leaves the door open to surprise. Close your eyes for a moment. Picture a gentle tug on a great web. Galaxies drift along the threads. They do not drift randomly. Many seem to head the same way. Long ago, astronomers gave one part of that tug a name. They called it the Great Attractor. The Great Attractor showed itself through motion. Galaxies near us do not move only with the expansion of space. They have extra speeds. Those extra speeds point toward a region in the sky. That region sits near the constellations of Hydra and Centaurus. It lies partly hidden behind the thick band of our Milky Way. Follow-up studies found a very rich cluster there called the Norma cluster. Norma is heavy and crowded. It looks like the core of a deep well of gravity. Now imagine another mystery. Some teams found a faint but common motion of many faraway galaxy clusters. They used the oldest light in the universe to seek it. That motion points to a patch of sky near Centaurus and Vela. Because the directions are close, people asked if the Great Attractor and the Dark Flow are the same tug. The idea is simple and tempting. But the scales are very different. The Great Attractor sits in our local neighborhood. It is tens of millions of light years away. Its pull affects nearby groups and clusters. By contrast, the Dark Flow claim reaches much farther. It was reported to stretch to hundreds of millions or even billions of light years. A local lump of matter is too close to explain a motion that seems to march across such vast distances. Part of the problem is our view. The Milky Way blocks a quarter of the sky. Dust and stars hide whole swaths of galaxies. This hiding place is called the zone of avoidance. For decades, astronomers worked to peel that curtain back. They used radio waves and infrared light to see through the dust. Surveys with infrared catalogs and with radio telescopes found many galaxies that were invisible in ordinary light. Those discoveries changed our map of the nearby universe. They also changed how we think about what could be tugging on us. Mass matters. Gravity comes from mass. To pull as far as the Dark Flow claims, we would need a truly enormous mass. Estimates for the Great Attractor are large but not huge enough. Some studies put the mass of superclusters and big complexes at many times, a trillion times the mass of the Sun. Even so, the numbers often fall short of what would be required to explain a coherent flow over 1 billion light years. That is why some scientists look beyond the Great Attractor. They point to still larger structures like the Shapley concentration, and to vast walls and superclusters mapped by modern surveys. History teaches caution. The Great Attractor itself was once a mystery. It took many surveys and many wavelengths to reveal parts of it. At first, the picture was incomplete and even misleading. The Dark Flow argument has followed a similar path. Early measurements used clever tricks to lift a faint signal from noisy maps. Other teams used different data and different filters and found less or none of the effect. The Planck satellite made the cleanest full sky maps so far. Its careful study put tight limits on large-scale bulk motion and found no clear evidence for the huge flows originally claimed by some teams. So where does that leave us? The direction match between Dark Flow and the Great Attractor is real enough to be noticed. But the simple idea that one nearby mass explains a distant pattern does not hold up easily. Either the tug has many contributors spread across space, or there are structures hidden or dim that we have yet to map, or the initial signals were overinterpreted. Modern maps of flows and new redshift surveys have shown us structures that are bigger than once thought. They have also shown that local motions are born from a tangle of pulls from many directions. If you listen to these stories, you hear two lessons. First, the universe is full of structure at many scales. Second, our picture of that structure depends on how deeply and how cleverly we look. The Great Attractor offered the first clue that our neighborhood is not simple. Dark Flow asks us to ask a bigger question. Is there a larger pattern out there that we have not yet fully seen? To answer that, we need more data. We need more maps. We need the patience to let careful measurements replace quick hopes. In the end, the link between the Great Attractor and Dark Flow is perhaps less a neat solution than an invitation. It invites us to keep searching through the dust. It asks us to add more voices to the conversation. The sky will not give up its secrets at once. It will yield them slowly. And when it does, we will know both the names and the size of the hands that tug on our little corner of the cosmos. I want to tell you a quiet story. It is a story about a small tug on a very big sea. The sea is space. The tug is the odd motion that some people call dark flow. We ask a plain question: what is pulling us? One idea is simple and bold. Something very far away pulls on our patch of the universe. It may lie beyond the part of the universe we can see. If so, its gravity would nudge whole clusters of galaxies in one direction. This is the sort of idea that grew out of the first measurements that found a common flow of clusters using the kinematic Sunyaev-Zeldovich effect. Those measurements were surprising and raised the question of superhorizon influence. A second idea turns to other universes. Some theories of inflation imagine our universe as one bubble among many. If another bubble rubbed against ours long ago, it could leave a large sway in the motion of matter. This would appear as a tilt or a preferred direction in the sky. People have tried to test that by looking for the marks of bubble collisions in the cosmic microwave background. So far, the direct searches have not found a clear collision. Still, the idea remains a way to explain a coherent motion that seems too large for known structures. A third idea reaches for heavy objects hidden in plain sight. Primordial black holes are black holes born in the first moments after the Big Bang. If some of these were very massive and rare, they could tug on nearby matter. They could also seed early structure. People study primordial black holes as dark matter candidates and as actors in structure formation. But the mass and number needed to pull on clusters across 1 billion light-years would be extraordinary. That makes this option unlikely unless we find new evidence for many huge primordial black holes. Cosmic strings are a fourth idea. They are thin cracks in space that some particle theories predict. If a long string threaded the cosmos, its gravity could drag matter along. Strings have distinct signs in the microwave sky and in maps of galaxies. Modern searches, including careful work by the Planck team, put tight limits on how strong such strings can be. Those limits make it hard for strings to be the main cause of a vast, coherent motion. Some researchers look at the dark energy and gravity side of the ledger. Maybe dark energy is not smooth. Maybe gravity behaves strangely at the very largest scales. If the cosmic push from dark energy varies from place to place, then motions could be biased. Or if gravity is different than Einstein thought on the biggest scales, then flows could look odd. These are active fields of study. They are wide and careful reviews cover many such ideas in depth. But so far, standard models and current maps fit well with a simple, smooth dark energy and with general relativity on large scales. Another class of ideas calls up exotic matter and unknown forces. This is the most open category. It says that some new particle or field could create a long-range pull. Theories here range from plausible to wild. They are hard to test because they need new kinds of evidence. Good science keeps them alive only as long as they remain consistent with data. So far, the data have not demanded a particular exotic actor. At the same time, the data have grown sharper. The Planck satellite made the cleanest maps of the microwave sky so far. Planck looked for the very signal that might show large, coherent flows. Its analysis put strong limits on large-scale motions and found no clear evidence for a dark flow at the strength first claimed. This is a heavy constraint. It forces theorists to make careful and modest proposals that fit all the maps. Some teams still argue the signal survives careful checks. A re-examination of WMAP and Planck maps by other authors found features that they say are consistent with a dipole at cluster positions. This disagreement shows the heart of the issue. Measurements are subtle. Different filters and different cluster lists change the result. The tug might be real, or it might be a trick of the data at the edge of what our instruments can do. So how do we rank the ideas? A step of honest common sense helps. Start with the ideas that need the least new physics. That means looking first for ordinary matter and known structures that we might have missed. Next, we test less ordinary options like heavy black holes or strings. Only if those fail do we reach for the multiverse or for new laws. This is how the best guesses become good ones. Data lead and fancy theories follow. What matters most is not which idea is prettiest. It is which idea fits all the facts. That is why more and better maps are coming. New microwave surveys and deeper catalogs of clusters will make the tests sharper. New statistical methods will cut down biases. With time, the field will sort the real tugs from the mirages. For now, the search is a gentle mix of wonder and caution. The visible universe keeps its boundary. Beyond that is the unknown. We can imagine a massive hand pulling from far away. We can imagine a neighbor universe leaving a scar. We can imagine hidden black holes or thin strings. We can also imagine that our maps are imperfect. The wise view keeps all of these in mind, and it waits for better light. They found a whisper in the sky. Then they heard the first echo of doubt. This is the story of how science responded when an odd signal called dark flow was reported. It is the story of careful checks and hard questions. The original claim came from a team led by Alexander Kashlinsky. They used maps of the oldest light and a long list of X-ray bright galaxy clusters. They stacked the tiny signals from many clusters. They reported a faint dipole aligned in a single direction. They argued that whole clusters seemed to drift together across vast distances. That result shook the field because it seemed to point to something beyond what our standard picture predicts. Skepticism arrived quickly. One clear and careful critique asked a plain question. How strong is the signal when the correlations inside the microwave maps are counted properly? This analysis found that once the maps and their channel correlations were treated differently, the claimed significance dropped a great deal. In simple words, the critic said the whisper might be no louder than the background noise. That critique opened a wider debate about statistical methods. The central worry was not malice, it was subtle math. The cosmic microwave background is itself a pattern. Filters meant to pull out a small moving signal can interact with that pattern. If those interactions are not fully modeled, then a false dipole can appear. Different teams use different filters, they use different cluster lists. They use different ways to estimate the noise. Small choices made large differences in the final answer. Then came a very careful test from the best full sky maps we have. The Planck satellite made the cleanest microwave view to date. Planck looked for the same kinematic signal. Its team used several filtering methods and a large catalog of clusters. Planck reported tight limits on large-scale motions. In plain terms, Planck did not confirm a massive coherent flow at the level originally claimed. The Planck work showed that instrument confusion and the intrinsic cosmic noise together make it hard to claim a strong detection. That conclusion did not end the argument. Some researchers returned to both WMAP and Planck maps with refined methods. They claimed the dipole at cluster position survives when the analysis is done in a particular way. They argued that the signal correlates with the most massive clusters. If true, that would reduce the chance the effect is a simple map artifact. This exchange made clear that much of the disagreement sits in the details of the filters and in how errors are counted. Systematic errors are the other big worry. Telescopes have beams. Beams have shapes that change with frequency. Calibration drifts can creep in. Electronic noise and the way maps are stitched together can leave faint imprints. Galactic dust and radio sources add their own patterns. All of these can mimic tiny motions if they are not modeled and removed well. The Planck study emphasized that CMB confusion and instrument noise limit how tightly one can bound a large-scale flow. There are also alternative explanations that do not demand new physics. The thermal Sunyaev-Zeldovich effect from the hot gas in clusters can leave signals that, if imperfectly removed, bias results. The random primary anisotropies of the microwave background can line up by chance with cluster positions. Foreground emission from our galaxy or from point sources can masquerade as motion. These are dull, ordinary effects. Yet they are powerful enough to fool us when we push measurements to their limits. Part of the answer lies in method diversity. Some teams measure kinematic effects using pairwise statistics rather than a dipole at cluster pixels. The pairwise approach looks at the relative motion between pairs of objects and so reduces some common sources of bias. High-resolution ground-based telescopes have detected the pairwise kinematic signal. That shows the kinematic Sunyaev-Zeldovich effect is a real, measurable phenomenon when the method and data match the question. But detecting pairwise motion is not the same as finding a vast coherent flow that points everywhere the same way. Reproducibility has been the crux. Some studies see hints, some do not. That split matters. A true cosmic flow must show up under different methods and with different instruments. It must survive changes in filters, in cluster lists, and in error estimates. So far, a robust instrument-independent detection at the strength first claimed has not been established to the satisfaction of the whole community. Bias from our place in space also shapes results. We live inside a web of mass that tugs locally. Local superclusters and voids imprint motions on galaxies and clusters nearby. Different surveys sample the sky unevenly. That can make a pattern appear when it is only a mirror of our limited view. Studies of peculiar velocities using galaxy surveys have found significant bulk motions on certain scales. These results show that large-scale flows happen, but also that measuring them is subtle and sensitive to how the survey was made. What would satisfy the skeptics? First, a clear signal that is found by several independent teams. Second, a detection that uses different techniques and different telescopes. Third, a careful accounting of every known systematic that could fake the result. And fourth, a match to other probes so that the motion shows up across the full web of data. That is a high bar. It should be high for a claim that asks us to rethink large-scale cosmology. In the end, the debate over dark flow is science doing its work. Someone sees a curious pattern. They publish, others test and question. Methods improve. New maps arrive. The answer will come when many threads point the same way. For now, the skeptics have given us a gift. They taught us how fragile faint signals can be. They taught us how careful we must be with maps of the oldest light. And they showed the path forward. More data and more methods will tell whether the whisper was a true voice from the deep or a trick of the sky. Science moves forward by testing. A claim is made, other teams try to repeat it. That is the quiet first step in the story of dark flow. Soon after the first reports, groups around the world tried to check the same sky. Some used the older WMAP maps. Some used the newer Planck maps. Some used ground-based telescopes with higher resolution. They all looked for the same faint kinematic fingerprint that the first team had reported. One long study compared the WMAP and Planck maps and kept finding a dipole signal at cluster positions, a result that kept the question alive. But then the most detailed full sky study came in. The Planck team ran many tests. They used several filters and a large cluster catalog. They found no clear detection of a huge coherent bulk flow at the level first claimed. Planck set limits on how big such motions could be. Those limits match what the standard cosmological model predicts for very large scales. Other careful voices raised a different worry. They looked at the math behind the first claim. They asked whether correlations inside the microwave maps had been fully counted. One statistical reassessment showed that when those correlations were handled differently, the claimed significance dropped a lot. In plain terms, the whisper might be hidden under normal cosmic noise. At the same time, the community learned that the kinematic signal itself is real and measurable by other routes. A landmark detection used high-resolution maps and a pairwise method to show that galaxy clusters move toward each other on average. That work did not claim a single giant flow across the whole sky. It did show that the kinematic Sunyaev-Zeldovich effect can be detected with modern instruments and that velocities can be measured statistically. This mix of results shaped the next phase. Teams sharpened their tools. New filters and matched methods took aim at the known pitfalls. Pairwise statistics reduced some biases. Cross-pairwise and bispectrum estimators have been proposed to squeeze more signal out of cleaner maps. Simulations now play a central role in testing whether a given analysis can produce a false positive. The telescopes coming online will help a great deal. Large projects like the Simons Observatory and the planned CMBS-4 will map most of the sky at high resolution and low noise. When those maps are paired with big galaxy and cluster catalogs from surveys like DZ and the Rubin Observatory, the power to detect or to rule out a coherent flow will grow rapidly. Forecasts show that these next-generation experiments will lift the pairwise and other KSZ measurements out of the murk and push the errors down by large factors. International teams are already building the pipelines and the shared catalogs needed for these joint studies. People plan to cross-check results with many methods. Ground-based telescopes, space telescopes, optical surveys, and infrared missions will be used together. That is the only way to beat the subtle systematics that can fool each instrument by itself. Computer simulations hold a key role. Simulations create mock skies with realistic noise and foregrounds. Analysts inject known bulk flows into those mocks. They then run their full pipelines to see if the flow is recovered or if a fake signal appears. This cycle of mock data and real maps is how teams show that a result is robust. So when might we know for sure? The honest answer is that the next decade looks decisive. Early science from the new observatories will arrive in a few years. The full combination of CMB Stage 4 depth and wide optical and spectroscopic maps will follow. If a true large-scale dark flow exists at the strength first reported, it will show up cleanly in those data. If it does not exist, those same data will close the door on that possibility. For now, the search is steady and careful. Teams rework methods. New instruments are built. Simulations test the methods. The field watches and waits for clear agreement between different eyes on the sky. When that day comes, we will know whether the universe was whispering or speaking. Imagine a quiet sea that looks still from the shore. You think the water rests. You think the world is calm. Then you feel the tug under your feet. A slow pull moves everything at once. If dark flow is real, the universe may be that sea. A hidden current may be moving whole swaths of galaxies. It may be gentle, it may be vast. It would change what we think we know. Our current picture of the cosmos rests on a simple idea. On the largest scales, the universe looks the same in every direction. The sky is not special here or there. This evenness shows up in the ancient light that fills space. That light is the faint glow left from the first fire. The maps of that glow look smooth, with only small bumps. Those bumps match the story told by the leading model of the universe. That model says space is almost flat. It says matter and light and a quiet pressure called dark energy shape the whole. The maps agree to a striking degree. They anchor the belief that the universe has no grand tilt. If dark flow is real, that anchor would shift. It would say the sky has a preferred way. It would say the cosmos is not as even as we thought. That would force a rewrite of our textbooks. Dark flow would also reshape the debate over the size of space. We can see only so far. Beyond that limit, light has not had time to reach us. We call that the horizon. If a vast pull tugs on clusters across the horizon, then something beyond our sight is at work. That would hint that the universe holds structure far larger than our maps. It would suggest a deeper layer of order outside our view. The flow would be a message from that unseen realm. It would tell us that the universe extends with patterns we can only infer. The first claims about this flow pointed toward a single patch of sky and suggested a motion that reaches across an immense distance. Those claims implied a cause that lies past the edge of what we can see. If such a signal holds up, the horizon is not a wall. It is a window with frosted glass. This possibility reaches back toward the first moments. Our best story says that the newborn universe grew with wild speed in a tiny sliver of time. That burst is called inflation. It stretched space smooth and flat. It set the seed for the gentle bumps we now map in the ancient light. But inflation might not be simple. In some versions, different regions can form with different fates. They can be like bubbles in a larger foam. If a neighboring region pressed on ours, the scar could be a gentle push felt across the sky. Dark flow could be that kind of scar. If so, it would be a hint that our patch had a meeting with another patch long ago. It would be the faint knock of another realm on our cosmic door. Searches in the sky have looked for marks of such meetings. They have set rules for what those marks should look like. If dark flow is real, it would add weight to this line of thought and give it a new target to test. That thought leads to a larger idea, the idea of many universes. The idea says that basic settings of nature might vary in different regions of a larger whole. These settings decide how stars burn, how atoms bind, and how galaxies grow. If these settings can vary, some places will make long-lived stars and life-friendly chemistry. Many will not. If dark flow points to structure or neighbors beyond our horizon, then the idea of many universes moves from abstract to testable in spirit. It would not prove the full picture, but it would show that our patch is not an island with no shores. It would say there is a wider ocean. Reviews by leading scholars lay out how such a picture could fit known physics. They show how this view might explain why some numbers in nature seem tuned for complexity to arise. A real dark flow would push those reviews into the heart of cosmology. There is also a link to a quiet but bold line of reasoning. It is called the anthropic idea. It asks why the world has properties that allow stars, planets, and observers at all. One famous step in this line argues that the strength of the silent pressure that speeds up cosmic expansion cannot be too large. If it were much larger, galaxies would not form. That argument, made long ago, gave a bound on that pressure before we measured it. If dark flow is real and tied to regions with different settings, it would lend context to that kind of argument. It would not end debate. It would show that selection effects might have a place in how we think about the cosmos. You may ask about dark matter in this picture. Dark matter is the unseen mass that shapes galaxies and clusters. It pulls with gravity, but does not shine. It helps set the web of structure we observe. If there is a huge pull across the sky, it could mean there is an enormous weight beyond our sight. It could be a sea of dark matter outside our horizon. That mass would tug on our region and create a flow. Our current maps already weigh dark matter through how it bends light and through how it built structure over time. A true dark flow would say that part of the mass that shapes our motion lies outside our maps. It would ask us to extend our models of how dark matter is spread on the very largest scales. It would change how we read the balance sheet of cosmic matter and motion. If the flow exists, it would also challenge precise checks of evenness made with the ancient light. Those checks say the sky is close to uniform. They set limits on large-scale patterns in that glow. They also place limits on any overall drift of matter. A real dark flow would need to live within those limits or explain why the old light does not show it plainly. That tension would push theory and data work to a higher bar. It would force us to refine how we extract tiny motion signals from noisy maps. It would make each assumption show its face. It would be science at its best, where a stubborn fact strains a trusted model until a deeper truth emerges. What would this mean for exploration? It would drive new surveys that map the sky more deeply and more widely. It would focus attention on tools that trace motion without relying on light from stars. The subtle shift that moving clusters imprint on the ancient glow is one such tool. Future experiments that sharpen that tool would be crucial. So would maps that track how mass bends light across the sky. New observatories are built to do exactly these things. One is a ground array that will read the ancient glow with far greater care. It aims to reveal faint signals of motion and heat in the gas that fills clusters. Another is a space mission that will map the shapes and distances of vast numbers of galaxies and weigh the dark matter that surrounds them. If dark flow is real, these projects will catch its signature and chart its reach. Such a discovery would ripple into how we plan missions. We would design surveys that chase the suspected direction of the pull. We would seek independent ways to test the same claim. We would compare the motion of clusters, the drift of background light, and the bending of distant galaxies. Today the question is still open. Some teams see hints, other teams do not. That is where we stand. The idea of one grand river of galaxies is alive, but it is not yet proven. Careful tests have cut both ways. That is normal in science. It is how we make progress. The story begins with the glow left from the first light. That glow is the microwave sky. It is smooth. It is also rippled by tiny hot and cold spots. Those ripples are a treasure map. They let us track motion in space. We do this by watching how hot gas in clusters nudges the glow. As fast-moving electrons in the gas scatter the light, they shift its temperature by a hair. This is the kinematic Sunyaev-Zeldovich effect. It is small, but it is real. It lets us sense motion without using a ruler or a clock. That is the key. A group led by Alexander Kashlinsky used this trick with many clusters. They looked for a common lean in the data. They reported a dipole. In plain words, they saw one side of the sky a touch warmer at cluster spots and the other side a touch cooler. That pattern matched a single flow. It pointed toward a patch near Centaurus and Vela. It seemed to reach deep into space. The claim was bold. It did not fit the standard picture. Yet the method was clever, and the signal was steady across years of maps. The team pressed on. They refined the way they filtered the sky. They checked for known sources of noise. The dipole remained in their hands. Other scientists raised flags. Could the filter itself make a fake wind? Could leftover ripples from the glow mimic motion? Could the catalog of clusters bias the view? A careful test in a leading journal put the brakes on. It showed that once you fold in the true mess of the microwave sky, the signal weakens. Planck then weighed in with its own maps and methods. It found no giant all-sky flow. It did find motions when you compare pairs of clusters and galaxies. But that is a different thing. Those are local pushes and pulls from nearby matter. They are not a single river that runs across the cosmos. So the community split into two camps. One camp says the dark flow picture is not needed. The other says the hints line up and we must keep looking. Both sides agree on one point. We need better maps, sharper tools, and more ways to cross-check. That is the work now. It is steady and patient. It turns big claims into clear answers. Fresh measurements of the tiny motion signal have grown stronger. Years ago, a team using the Atacama telescope saw the first firm sign of the pairwise effect. Clusters that fall toward each other give a small but clear mark in the glow. Later, a team that joined the South Pole telescope with the Dark Energy Survey saw the same thing with more weight. Planck also caught the pattern in a different way by tracking how hot gas around central galaxies shares a common push. These results prove the method. They show we can measure motion from the sky itself, but they do not yet show one vast flow. They tell us our tools work. Now we ask them a deeper question. New machines are coming to help. The Simons Observatory is built to read the microwave sky with very fine eyes. It will map huge regions and pick up the faint motion marks with care. It was designed with the kinematic signal in mind. The forecasts show large gains in how well we can turn those tiny temperature steps into clean velocity maps. A later project known as CMB Stage 4 aims to go even further. It plans many small dishes and wide scans. It will reduce noise and confusion. It will let us push motion studies to larger scales and earlier times. With these two efforts, we will move from hints to tests that can break the debate. We will not rely on the microwave sky alone. A new space telescope named Euclid is now surveying billions of galaxies. It measures shapes and distances in one deep sweep. Its maps of matter, together with microwave maps, make a powerful pair. With both in hand, we can try a method called velocity reconstruction. In short, you use the layout of galaxies to predict how they should move. Then you compare that predicted motion to what the microwave sky says. Any leftover trend can be tested as a true large-scale flow. Euclid has begun to release early data and plans. The scope and quality are clear. The reach is vast. Ground surveys add more fuel. The Rubin Observatory will watch the sky night after night for many years. It will build a deep and wide movie of galaxies and supernovae. Supernovae let us probe bulk flows in a very different way. They serve as standard candles and can reveal if space has a preferred drift in the nearby cosmos. Rubin will give us far more supernovae than ever before. That means tighter tests and better checks for bias. On the theory side, new ideas help us read the data. Work on kinematic tomography shows how to join galaxy surveys with microwave maps to pull out the velocity field. The math is subtle, but the result is simple. You can rebuild the hidden winds that shape clusters and filaments. If a giant one-way push exists beyond our horizon, it should leave a trace in these reconstructions. If it does not, the maps will show only the local churn we expect from normal growth of structure. The key is to compare many independent slices of data and see if they point the same way and with the same speed. Young scientists can jump in. Much of the data is public. Planck maps are open. So are many catalogs from past and present surveys. The tools are shared as code and notebooks. Students can learn by repeating older tests, then trying new filters, new masks, and new ways to mix data sets. Small teams can make real gains by finding better checks for noise, or by tracing how dust and radio sources might hide in the signal. Skilled work on a laptop can matter as much as telescope time. That lesson is one of the gifts of this field. The public has a stake as well. This question goes to the heart of where we live. If there is a pull from beyond our view, we learn that our patch of space is part of a larger pattern. If there is not, we learn that our standard picture still stands tall after yet another hard test. Both outcomes are wins. Both sharpen our sense of how the universe works. Both feed the drive to ask the next question. We must also be ready for a twist. It could be that what looks like one flow is a mix of smaller ones. It could be that a quirk in how we clean the maps plays a role we did not grasp. It could be that new surveys will show slight bends that point to known physics, rather than anything beyond our horizon. Or we might see a clear, coherent, deep signal that lines up across methods. Science is a slow sieve. It keeps what is solid and lets the rest fall away. So where do we go from here? We keep measuring the tiny temperature shifts around clusters with better beams and lower noise. We keep cross-checking with galaxy maps, lensing maps, and supernovae. We make mock skies and run them through our full pipelines to see what tricks the data can play. We write down in plain words what would count as proof and what would count as a refutation. And we share every step so others can repeat the work. That is how the field moves. In the end, this is a human story. We look at a quiet glow on the sky and try to hear motion in it. We argue in good faith. We test. We fail. We learn. We try again. Someday soon the maps will be sharp enough and the methods will be strong enough. Then the answer will be simple. Either there is a great pull beyond our sight, or the universe is as even as we have long believed. Until that day, the search itself is a light for us. It reminds us why we do science at all. It is the joy of turning wonder into knowledge, and the work never truly ends.